Good news. The final lecture today. Okay. All right. Okay. To come out with a good control law, understanding the system to be controlled is a crucial first step. Okay. A deep grasp of the underlying physics is essential for developing control laws that are both effective and reliable. Okay, so this is very important for control engineer. To control a system, we need to control my system I want to control. I need to have a very, very good knowledge, deep understanding of the behavior of the system. This is very important, all right? Now, here in this PowerPoint slide, I want to emphasize that feedbacks needs a sensor, okay? Now, this is sometimes a disadvantage of feedback control system. Why? Because since you need money to buy sensors. So apparently, for this very reason, feedback control is typically much more expensive and also much more complex than the open loop control. All right. The other thing, I will talk about the other limitation later. Okay. Now, in this block diagram, what I want to emphasize that this is the basic. This diagram illustrates the basic structure of feedback control systems. Based on these basic structures, you can come up with many advanced variations. For example, here is one advanced variation. Here you have two feedback loops. Why you want to do that? There are a bunch of reasons. But the basic idea is that, for example, you have a system which integrate mechanical parts and electrical parts, all right? And typically what happens is that the time constant, that is the speed of response of mechanical system, is much slower than the speed response of electric system, right? Okay, that is why nowadays electrical vehicle, when it comes to acceleration, typically it's easily outperform traditional gasoline-driven vehicles. Okay, so if these two systems have different time constants, that is different speed of response, then typically it requires two control loops. One for the slower mechanical subsystems, the other for the faster electrical subsystems. All right. Now, another variation is that what we saw before is a single input, single output system. But in reality, your system can have multiple input and multiple outputs. Why is that the case? This is a good example. This is a generator which will convert. Let me say it's a power generator. It will generate electric energy based on by burning fuel. Now here is the boiler. The input of boiler including water, including fuel, including air. Okay, and the boiler will send its output to the turbine, which will drive the shaft to the generator to generate electric energy that we want, and to monitor the operations of the entire process. We need to measure oxygen. We need to measure temperature. We need to measure pressures. We need to measure the speed of the turbines, and dynamically and adaptively adaptively adjust all these physical variables so that the power generation, the efficiency of the power generation can be maximized. So by its very nature, it's a multiple input, multiple output systems, all right? But I want to emphasize one thing is that in this course, our focus is on single input, single output system, which apparently is the building block of MIMO systems. Now, here, the next important element of this course is about uncertainties. Why do we need feedback controls in the first place? The answer is uncertainties. What kind of uncertainties we will run into? There are basically three different possibilities. One is input disturbance, the other is parameter variation, and finally, the measurement noise. Okay. Now, first of all, I want to emphasize again, okay? Remember this fundamental diagram of a feedback control system, which consists of four subsystems: controller, actuator, process to be controlled, or the object to be controlled, and the sensor, okay? Now, what is an input sensor? Let's say you have a bipedal robot, which can move around. And let's say you want to apply a force to it, okay, to make the robot fall. And if the robot has a good feedback control system, it will somehow compensate this disturbance and maintain its stability, all right? And we will run into all kind of input disturbance in reality. For example, in the cruise control systems, okay, the goal here is to maintain the speed of your vehicle at a set speed, right? But you will run into different kind of uncertainties. For example, you may come into a road condition which is keep going higher and higher, or keep lower and lower, okay? And that will generate gravitational force in different direction, okay? And you will run into different road conditions, okay? You will probably drive your car against the wind, all right? And that will let your car run into more resistant force, okay? So an automatic cruise control system have to somehow compensate those input, so-called input disturbances. This is another example. I said it many times. Human body has many built-in feedback control systems. For example, when I'm lying down, everything is cool. I feel comfortable. And suddenly I think I should stand up and do something useful. So I stand up, okay? Now, one thing our heart needs to do is to pump the blood into every part of our body, right? Okay, and one of the most important part of our body is our brain, okay? Once I stand up, something changed. When the heart pumps the blood into the body, okay, here, it does not run into any gravitational force, right? When I stand up, then there is a gravitational force pulling down. So my brain senses that change. So it sends a signal to the brain, and brain sends a signal to the heart. The point I want to make here is that my body need to increase my blood pressure in order to counteract with the negative impact of the gravitational force. And if my brain heart blood pressure control system is not functioning properly, is not functioning fast enough, then my brain will not receive sufficient blood flow, and I will feel dizzy. Okay, but probably after a while, okay, after my blood pressure control sense do their jobs, okay, and I will probably feel less dizzy. So the reason when I feel dizzy when I stand up is because my blood pressure control system cannot function properly. It cannot react fast enough. Okay, so our control systems is a very good mirror. The control system in our body, how it functions, is actually a very good indicator, a very good mirror of our health. Okay, let's skip this PowerPoint slides. Now, the next issue about the next possibility of uncertainty is parameter variation. Okay, for example, when designing a adaptive cruise control system or just simple cruise control system, you have to make an assumption about the weight of your vehicle. Say it's let me say 102 kilogram to 800 kilograms, depends on number of passengers, right? But that may vary, okay? It changes from case to case. And this is just overwhelming possibilities, okay? For example, when you design a feedback control system for elevators, there is no way you can make sure the number of the passengers, the overall weight of the passengers, okay? So that is an additional uncertainty, and that uncertainty exists all the time. It is the job of the feedback control system to take care of that uncertainty. I mean, the impact of the uncertainty, the impact of parameter variation will always exist. But how can I compensate it? How do I minimize those impacts? Become a very important duty for the feedback controller, okay? This is another type of parameter variations, okay? We are just getting heavier and heavier, okay? Now, the point I want to make here is that sensor is like the eyes of a control system. Its speed and accuracy is of vital importance for control systems. Because without the system, you have no idea about the real actual condition of the system. However, this is also, I think, the weakest point of a feedback control system, which is the reliance on sensor. Why? Because sensor, like any mechanical or electronic devices, it will have error, and it can produce error, okay? Once you have error, okay, once sensor has error, there is no way a feedback control system can compensate that error. Why? Because the sensor tell me what the operation condition of the processor is, what the condition of the processor is. And remember that the entire principle, the basic philosophy of feedback control system is output driven. I do everything based on the output error of the feedback control system. If this information is false, is misleading, is incorrect, then what I do will all drive me to go to the different direction, and typically wrong direction. And there is nothing I can do about it because I have no idea that the information is false. So the reliance on the sensors is the weakest point of feedback control systems, because once the sensor cannot provide accurate information, the feedback control system is doomed. Okay, there's nothing it can do to help itself get out of trouble. Okay, so when building a real control system, okay, many people put emphasis in the development of controller. That is, of course, very important. But as a control engineer, I think the first thing I need to do is to make sure my sensor is solid, it's reliable, it has been calibrated to provide maximum accuracy, because everything I do in the future depends on it. If it provides me false information, then I will definitely, more than likely, not definitely, but more than likely, go into the right direction. Okay? All right. Now, let's get a real world example. Okay? Let's talk about the state condition of Taiwanese. Okay? This line represents the number of sleeping pills over time. Okay? This blue line represents the number of persons who were taking sleeping pills. Okay? As you can see, Taiwan only the population of Taiwan is 23 million. Okay? Here, every year we take 8,000, almost 9,000 million sleeping pills per year, very close to 1 billion. And our government told us that this needs to stop. Okay, they will watch it, they will monitor it, they will advise the doctors, the hospitals to control the use of sleeping pills. And it didn't work. Right now, nowadays, the number of sleeping pills we take each year is already over 1 billion per year. Remember, the population of Taiwan is only 23 million, and we take more than 1 billion sleeping pills per year. What does that mean? What that means, that pill is not effective. If the medicine is effective, I take that medicine for a period of time, and I'm supposed to be cured. I'm supposed to be recovered from my disease. Why do I have to take that pills? It means my disease has not been cured. I have to use that pill to control my condition, not curing my disease. Why is that the case? Because the problem of insomnia, that is the problem of not able to fall asleep, right now is an open loop control. Because after receiving the sleeping pills from the medical doctors, I take the pills, what happened? The doctors have no idea about my sleep contents, have no idea what the medicine, what the sleeping pills do to my body, do to my sleep conditions. He has absolutely no idea. Why? Because he has no sensor. He has no information. Then, of course, as a patient, I can report to the doctor what the sleeping pills do to me, right? But that often is in practice, and the reality has demonstrated that again and again and again. The information provided by the patients are not useful. Why? Because sleep itself is not a sober process. During sleep, our head is not clear. We cannot think clearly. We don't understand our conditions. So the condition I report is inaccurate, unreliable, and unuseful. So we just keep doing this open loop control, and things just keep getting out of hand. But the ideal condition is that we should turn it around into feedback control. That is, patient is the process to be controlled. and the sleeping drugs inductor by lump them together should be the controller and actuator, okay? And we should have a sensor to monitor the condition of my sleep, or my sleep contents, the sleep efficiency, the latency, the sleep architecture, okay? How much deep sleep I have, how much REM sleep I have, okay? How many times I wake up during the night. We should have that kind of sensor. Okay, smartwatch can do something about it, but it's not very accurate. Okay, so we need to have good sensor to close the loop. All right. So once the loop is closed, I think the performance of the system can be elevated to another entire different level. So converting a system from open loop to closed loop, everybody know, or at least a lot of people know, is often a solution to many different problems. Okay, but I think we should extend that understanding to many different areas of our life, including sleep medicine. Okay, all right. Now, the next issue I want to talk about is about performance indices. All right, that is, how do I characterize the performance of a system? Okay, I divide the performance indices of a control system into 3 levels. The first level is absolute stabilities. That means every variable of that control system, their values has to be bounded. That is, it will not diverge as time progresses. Because for any mechanical system, if any stress, any strength, any temperature go up to infinity, that system, that mechanical system will definitely crash. Any circuits, if any part, any element of the cross voltage or circuit currents of any part of that circuit goes to infinity, that circuit is definitely will burn, right? So absolute stability is of vital importance, the very fundamental requirement for feedback control system. And the second part of the second level of the performance indices, including speed. I want the system to be fast. The second, accuracy, okay? I want the temperature to be 25 degrees Celsius. Then the tolerance should be as small as possible. Let's say minus or positive 0.1 degree. Now, minus and positive 1 degree, 0.1 degree. I prefer 0.1 degree than 1 degree difference. The second is relative stability. Okay, you have absolute stability, you have relative stability. I will compare these different type of stabilities in the upcoming slides. And then it's robustness. What is robustness? Robustness characterizes the sensitivity of the performance of the system with respect to uncertainties. Okay? The behavior, the performance of a person can vary depending on the pressure he is facing. All right? If everything goes well, let's say I'm a basketball player. I'm a good basketball player, and I play basketball very, very well. Okay, usually. But when it goes to the playoff season, the pressure build up, and my performance certainly drop. Then I'm not a robust basketball player because my performance depends heavily on the outside pressure. Same thing happened to control system. If a control system is robust, like I said, uncertainties will have an impact on the performance behavior of the system. But if the system is robust, it is relatively insensitive to those uncertainties, okay? So we want to minimize the sensitiveness to those uncertainties. So this is the reason why we have this criterion of robustness. Now, on a cellular level, we want a system to be adaptive, okay? That is, it can switch, like for example, it can switch to different operation modes under different circumstances. And sometimes, if possible, we want to perform optimization. That is, after guaranteeing the speed, the accuracy, the stability, the robustness, can we do something about the system so that the energy consumption of the system can be minimized? Because that, of course, can generate some financial reward. Okay, so stability, accuracy, speed, robustness are 4 different aspects of the control system performances. Now let's talk about stability first. Okay, when it comes to stability, first thing we want to make sure is that, for example, a boat cannot sink. Okay, an aircraft cannot lose its speed and crash. Okay, and absolute stability answers the fundamental questions. Will the system output remain bounded for bounded input return for a bounded input? Okay, now so to make sure our system has to be absolutely to have absolute stabilities, one criterion is that its output. As a matter of fact, every variable of that system, okay, has to be bounded as time progresses. Okay. All right. This is very important. Let me go back one step. When I was a graduate student, my advice professor, when he taught the course of control engineering, he told his students, myself included, that there is no stability when it comes to the definition of stability. So stability in this way, it doesn't have a definite definition. This is only one definition. Okay, this is one only definition, but it is a very good definition. Okay, that is every part of this, every variable of that system has to be bounded. Its variable has to be bounded. It cannot diverge. Otherwise, the system will crash, and that is a disaster because people will die. Okay. All right. The relative study answered different questions. How stable is the system? Okay. And quantify the margin of safety or robustness of an already absolutely stable system. Okay. For example, when driving a car, you want to guarantee absolute stability so your car won't crash. Okay. Or run into anything. But at the same time, you want to have relative stability. That is, you want your car to move in such a smooth, comfortable manner. You don't want it to vibrate all the time. Okay, you don't want it to give you a sense of insecurity because it's inaccurate, unstable movements. All right, so these are 2 different aspects of stability. Okay, now let's look at the response of a system. Okay, this, as you will see in the future, is what we call step response. Okay, let's say this is time and this is room temperature. Okay, you turn on air conditioner and then you watch how the room temperature change. Okay, now let's say you are in a winter and originally the room temperature is very low. Okay, you turn on the air conditioner and you set a desired room temperature, and the room temperature, the actual temperature of the room can increase in this way, okay? This is slow but stable response. Then it can increase in this way, or it can increase in this way. Okay, as you can see, the differences between these three curves. The first thing is about speed. This is the slowest, this is the fastest. The second difference is about stability. Here, you have acceleration. Here, you have overshoot. You have undershoot. Okay? In this operating condition, you will feel less comfortable because in some time, the room is simply too hot. And in other moments, the room is it's just not warm enough, all right? But here, okay, the temperature is relatively stable. So compared to the rig operating condition, it has better relative stability. What is the price to pay? Apparently, speed. So speed and stability are often two compromising factors that you have to consider. That is like driving a car. If you want to go over a corner, if you want to drive very fast, then your car will be less stable, right? And vice versa, all right? So speed and stability are often two compromising factors. You have to sacrifice one for the other. And therefore, you have to keep a good balance between these two factors. The other is accuracy, all right? Accuracy means that my output, the difference between my output and input, this error can be minimized. The smaller the error, the higher the accuracy of my control system. And the other is, of course, speed, okay? When it comes to speed, I can classify system into instantaneous and dynamic system. What is an instantaneous system? Like this gear train. I have an input gear, I have an output gears. The reason I want to put them together is I want to change the direction as speed or torque ratios of my input and output, all right? Assuming that among these gears, there is no any backlash. So whenever you make a rotate this shaft, and the output shaft will rotate accordingly, okay? You move it faster, the output shaft will move faster. In moving, you turn its direction from counterwise to clockwise, and the output gear will respond accordingly. There is no time delay, okay? There is no latency, okay? Everything from input to output just happen instantaneously. So controlling such an instantaneous system is, under such a circumstances, is really a piece of cake, because whatever you want in the output, you can adjust the input and you'll get it instantaneously. However, a dynamic system is not the same. A dynamic system typically has some energy storing elements like masses, spring, capacitor, or inductors. So as a result, it has membranes, which means its output will not, for example, in an instantaneous system, one of the big features of this system is that the output only depends on the current input, all right? It does not depend on the past history of the input, okay? Now dynamic system, on the other hand, has membranes, which means the output will not only depends on the input, but also depends the history of the input. Why? Because the system have energy storing elements. It would therefore has a memory of the past input. So the current output depends on the history of the input and not just its present value, okay? So consequently, dynamic system cannot be described by algebraic equation. Typically, for instantaneous system, all you need to do is set out the algebra equations, and then you can describe the relationship between the input and output. But for dynamic systems, that's not good enough. To establish a mathematical model, what you need is typically differential equations to model the time-dependent behaviors, okay? Now, for example, when you want to take a shower, okay, it's a demonstration of a dynamic control system, okay? You want to take a shower during the cold winter day, okay? You want the water to be hot, so you can have a comfortable shower. But that is not what happened. You turn the water on, the water will come out, but the temperature is not warm. It's not hot. It's icy cold. It would take a while for the temperature of the water to go up, right? And if I'm not patient, I just turn the temperature higher and higher and hope that the temperature of the water will rise fast enough. But typically, I will run into overshoot. The temperature of the water is simply too hot, so I have to turn it down again, all right? So this is a very good example of a dynamic system, okay? You will encounter overshoot, you will encounter undershoot, and things like that, all right? All right, the final dimension of the second level of performance index of control systems is robustness, okay? And it means that we need to be less sensitive to, let's say, outside criticisms or outside pressure. Similarly, control systems need to be less sensitivity to uncertainties. All right, okay? So the very reason we need feedback control in the first place is to compensate the effects of those uncertainties. That is, when we run into the inevitable circumstances of these uncertainties, our feedback control systems need to minimize their influences so that the output of these systems can conform to my specifications, all right? So the very first reason for feedback control system is to conquer, to compensate, to overcome the impacts of uncertainties, which include input disturbance, parameter vibration, okay? Measurement error cannot be killed by feedback control, okay? Feedback control cannot deal with the measurement noise problems. Once I have made measurement error, it will feed back directly to controller, okay? And controller will have no idea about how wrong, how inaccurate the measurement is, okay? So it's really the weakest part of feedback control systems. Now, people, sometimes you will hear me repeat the same thing again, okay? It's not because I'm too old. I have problem like dementia or Alzheimer's, and it's not that, okay? It's if I repeat the same material again, there is only one reason. I do that on purpose. The reason I want to repeat the same thing again is the thing that I repeat is the things I think of critical importance. By repeating them, I hope you can get so familiar, get so sick of these repetitions. But finally, you can learn them by heart. You never forget it. Okay. Okay. All right. Now, so robustness is a crucial measure of how well control systems perform when faced with inevitable differences between your theoretical plane model and the actual physical hardware, and all that model uncertainties and all other uncertainties. All right. Now, let me give you an example, and this example is a real example. Okay, this is cerebral auto regulations. Okay, remember blood pressure is very important, right? If my blood pressure is too high, I may run into problem like stroke or myocardial infarction. Okay, both of diseases are very, very, very dangerous. Okay, all right. Okay, now remember that blood pressure exists everywhere in our body, right? Okay, my body blood pressure will go up and down. There is another place blood pressure is of critical importance. That is the blood pressure of our brain, right? The blood pressure of our brain should be as constant, as stable as possible, all right? And we have a special name in our medicine for blood pressure within our brain. That is called cerebral blood flow, okay? Now, the thing is, blood pressure can go up and down, right? Depending on my physical conditions. For example, if I'm exercising, my blood pressure probably will go up. If I'm under a lot of stress, my blood pressure will probably go up, all right? But for our brain, that is not acceptable. So our brain, our body will try to regulate this blood flow within our brain as constant as possible, okay? So this is the region of the blood pressure that our body can maintain the cerebral blood flow constant, okay? And this is very important. If the blood pressure is simply too high, of course, the cerebral blood flow will inevitably go up and down, all right? But the stronger you are, the healthier you are, this interval, the wider this interval, that is, your brain, your body is more robust to blood pressure, okay? And this auto regulation property is of critical importance of our body health. For example, if I'm a patient, okay, who suffers stroke, then this region will be much slower, or sometimes it will shift, okay? Okay, and these two slides, let's just skip them, okay? Now, this is the curve. This curve is for a normal person, and this curve is a patient suffers from acute stroke. So as you can see, the performance of its feedback control system for auto-regulation of the cerebral blood flow has go way down. Okay, it just lost its functionality in regulating the cerebral blood flow under the variation of body blood pressure. Okay, now, all right, I think that's good enough for today's lectures. Okay, any questions? Okay, any suggestions? Okay, if you are too shy to raise them in public, you can always come to me, and we can talk to one another. Okay, we can always talk to one another. Okay, thank you for your attendance. Okay, 好，谢谢。
谢谢。